So today we are going to analyze our products, and I say this every time, but especially on this one, I think the worksheet that you got to do for this one, you got to read it 3 times, and it's a little bit longer. I'm going to learn to stop my yapping in these things, but yeah, it can be a little bit confusing. I think hopefully I'm going to nail down some of the theory here just right now. But also that worksheet, you read that 3 times, you should be pretty dialed in. I'll tell you one place that it seems to catch students a little bit off guard on this. In that worksheet, there's an NMR of the starter material, ethylacetoacetate, and then there's an NMR of the alcohol product. Okay? The alcohol product, yeah, it's a mixture of enantiomers, but NMRs of enantiomers are identical. So you don't even, it's not like you're going to see 3 things. You're not going to see the starter material and then 1 alcohol and 2 alcohol. Both alcohols, wedge and dash, get the same NMR. But so it is an NMR of 2 things. It's an NMR of your starter material, it's an NMR of your product on top of each other. So you should be able to look for all the signals of your starting material and find them in your NMR. And you should look on the worksheet, be able to see all the signals for the product and find them in your NMR. Might be small, you know. If you didn't get much product, then they might be kind of little itty bitty. If you got a lot of product, hardly any starting material, you know, those ones might be little itty bitty. But the NMR that you guys are processing is a mixture of the 2 of them. Okay? Does that make sense? Okay. And we always, I did it, if you had me for a semester, I always draw a structure, and then you draw, or you write letters or numbers identifying the unique types of carbon on your molecule. And then you put them on your product on the spectrum. Okay? Oh, yeah, this methyl here, it's got no neighbors, so it's a singlet. Ah, there it is. Boom. I put a little lowercase a, put a little lowercase a there. And I did that on the starting material one in the worksheet. You'll see all the letters. And then I did that on the product too. You'll see that. And so that's what you're going to be doing. But you're going to, I think it's about 5 signals for the starting material, 5 for the product. So yours should have 10 signals. Okay? So lots of letters or something. Does that make sense, guys? All right. Okay, I just realized I don't have glasses. Maybe. Getting old is awesome. Okay. Yeah, and if your reaction didn't work, I just need you to email me and say, hey, Gideon, need data. No problem. No, I'll get you data. You know, don't worry about that. No part of your grade in this class is ever going to be based on your ability to make 2-hydroxy and I forget how to name it now. Anyway, it's not on your ability to make these things. Unfortunately, if your NMR, you don't got product, and that happens sometimes for whatever reason. Especially, we didn't. After you guys, I cut the reaction time lower. So, fingers crossed that anybody got it. But if the NMR looks like, it doesn't look any good, doesn't look like this doesn't look right, then really your optical rotation is going to be meaningless too. So I'm going to need to generate both of those for you. All right. Okay. So the goal is that for today is we want to figure out the ratio. That's the ultimate goal. We want to figure out the ratio of R to S. And not only that, but we want to figure out which one is dominant. Okay? So, goal be able to figure out if it's R and S, and then on the worksheet you're asked to draw it. So you're going to have to go, oh, okay, R would be the wedge, or R would be the dash, or whatever it is, so forth and so on. Okay, so you might have a ratio of 70-30. Sometimes for this experiment, the ratios are pretty poor. Okay, like I said, this is not really fancy chemistry that would give you much better selection. Okay, so, but again, that's a reflection of the type of experiment, not the experimenters, not the scientists who did it. Okay. Yeah, and you know, so we've made enantiomers, and they only got one chiral center, so it is just R or S, right? It's not a matter of, you know, if you have multiple chiral centers, then you can't really describe it that way. You'd have to describe it. A lot of the time we'll say, you know, enantiomer A and ent A. Ent A, and I'm going to use that terminology here. Ent A simply means it's an enantiomer. A is an enantiomer. Okay? Remember, in an enantiomer, all the centers are the opposite configuration. So I can write a RRSS, and you automatically know that the enantiomer of that is SSRR, right? All right. Okay. Now, so the ultimate goal is the ratio. There's another way of describing sort of which one is in majority and to what degree it's in the majority, which is percent enantiomeric excess. Have you guys remember that concept a little bit? Okay, so that's okay. I have a very sad analogy from my own life that will drive this concept home. You will never forget it. This is very sympathetic. It's not that concept. But so, once you're comfortable with that concept of an enantiomeric excess, you can go back and forth between, and we call that percent EE a lot of the time. You can go back and forth between percent EE and ratio, or ratio to percent EE. Flip back and forth. That's going to be important because as we're going to see in a second, ultimately, what you get from the polarimetry is you get percent EE. Okay, I'll show you how, but that's what directly you generate by examining the results of your polarimetry. Okay, you get percent EE. After we go over this, you're going to be able to go from percent EE to ratio like that. Okay, which is the ultimate goal and in the work. Okay, make sense? All right. Okay, so all right, let me write this up. You can, and soon you will too, convert ratio back and forth to percent enantiomeric excess. Okay. So let's just quickly come up with just kind of a working definition of percent EE. That's the abbreviation. Percent EE, all right, is what is the excess of the major, okay, RS in our case, because there's only one power center. What is the excess of the major if all of the minor is paired up? Okay? Does that ring a bell, kind of? Okay, so here's my analogy for you real quick. These are my junior high dances. Okay? Way back. We would ride in on our carriages. No, it was cars. And for whatever reason, I don't know why, but there was always more boys than girls. Okay? But, so there's more boys than there are girls, so that's our major enantiomer in this analogy. Yeah. And the girls and pretty much all the girls would get paired up and they would be dancing. Okay. And then me and the other geeky kids would be lined up against the wall like this, just looking like, how do I do that? I don't know how does that happen. So we were the percent excess of the major enantiomer. Okay? The other enantiomers, the two enantiomers are all paired up out there, and we're the percent excess. Okay? Does that make sense? Okay. I think high school is the first time. Right? Anyway. All right. Okay, so let's do an example real quick. If you have 70%, let's say this is your ratio, 70% is compound A, okay? And thus 30% is nth compound A. So it's an enantiomer, okay? What is the percent EE? Any thoughts? Okay, 100 kids at Gideon's junior high dance. There is 70 boys and there are 30 girls. Okay. All of the girls are paired up. Okay. Some of the boys obviously are not. They're up against the wall. Okay. What's the number of boys up against the wall? Would you?
It was 40.
40. Yeah, 40. So that's the percent EE. Does that make sense? Okay. All right. But like I said, you want to be able to go back and forth. And also, go from percent EE. Okay, to ratio. Let's do it. Alright. Example, if you have 60% of, or 6% EE, sorry. Of nth compound A, okay? What is the ratio? So hard, 8:30 on a Monday morning. Coffee hasn't really kicked in. The Red Bull or whatever, the Monster. No, folks. Any thoughts? Make me go back to my dumb example. If you have 60% EE, it means that 40% is a 50-50 mix of nth and compound A. Okay. 60% is pure nth compound A. Right? And the other 40 is a 50-50 mix of the two. So what's your ratio? this was my son, and I ask him a question, and then I don't let him off the hook. I just sit there because I think that's where the synapses are right now. They're like reaching out, on to the next girl. But I don't know much about neurology, but I think that's how it works. Yes, Gina, thank
Is
you.
it 20%? Is it 20, like,
Well, what's the ratio of compound A to nth compound A, or nth compound A to N?
you said it was 50-50, right?
If you have a percent EE, it means 40 of it is a 50-50 mix.
Oh, okay, okay.
Yeah. I think you're awfully warm.
I'm thinking it.
So what's the ratio?
2 to 1.
What's that?
2 to 1.
No.
1 to 4.
What's that?
1 to 4.
It's 80-20 is what I'm thinking, which is 1 to 4. Yes? No. Yeah, it's 1 to 4. Yeah, yes, 1 to 4. Very good. Right. You know, so you have, let's see, how about I put your answer? Right now we're too early. Okay. 40% is pairs. Okay. So 20% and compound A. 20% compound A. Okay. So 20% plus the 60% that we already knew was nth compound A. So 80% nth compound A. 20% compound A. Should change these notes and get rid of the nth. That makes it not very fluid. Does that make sense, guys? Should we do another or move on?
Okay.
Okay. All right. So, but you do need to be able to, I mean, it's a good thing just for, students taking organic chemistry, maybe going to take an MCAT, I don't know, percent EE. I wouldn't be stunned if that showed up on some impact, It lends itself nicely to multiple choice. So, all right. Now, got to figure out. Let's see, what am I got a couple more things we got to figure out. What am I going to talk about? Okay, so how are we going to figure out the percent EE? Well, it turns out we can get that directly from optical rotation. Okay. You may remember that one of the only physical characteristics that enantiomers differ by is how they rotate light. It's technically how they rotate plane polarized light. There are all these planes of light. You send it through a filter that only lets one plane go through, and then it goes through your sample like this. And if your sample has an excess of 1 enantiomer, or let's say it's enantiomerically pure. It's all just 1 enantiomer. Then it will rotate it, one direction. Okay. And it will rotate it to a certain degree. And it's really hard to have it. There really isn't like a reliable way of looking at the structure and go, oh, that's going to rotate it a lot, or that's going to rotate it a little. Different molecules rotate it to different degrees. Okay. But so you got 1 enantiomer, it comes through, it rotates it to a very specific degree. Okay. There's some other factors that can influence how much it rotates it, but we'll talk about that in a second. But then, if you know that degree, what do you know about its enantiomer in terms of rotation? What do you know about its enantiomer? 1 enantiomer. The other enantiomer rotates in the opposite direction the exact same degree. Okay? It's one of the only ways they're physically different in the enantiomers, right? They're physically different in how they attach to receptors. That's like the thalidomide story we talked about. But they're all the same, and they're the same in like melting points and boiling points, how they appear on NMR, so forth and so on. Sometimes they crystallize different. Okay. All right. So, oh yeah, let me. All right. So, one enantiomer goes one way, another enantiomer goes the other way. All right. What if you had? And by the way, it has to be a chiral molecule. Achiral molecules don't rotate. It has to be chiral. What if in my mixture, as the plane light's coming through, what if I had a 50-50 mix of both enantiomers? How will this thing rotate? Just, it's not even, just what's your intuition about it, even if you don't, there's no. What's that?
It wouldn't rotate?
It wouldn't rotate, yeah, exactly. The light, I mean, the way you could think about it, I don't know if this is reasonable, but from my pea brain it works. You know, it's hitting each molecule and it's getting turned a little bit, it's getting turned a little bit, but because it's a 50-50 mix, they end up canceling each other out. So but if there's an excess, if there's a mixture of the two, okay, but it's not 50-50, all right, then it will rotate towards the major. In my last example, and A, it would rotate towards that. Okay, and without giving you the details, just the big picture is the degree to which it rotates compared to the known amount that it rotates if it's pure, if you don't have any of the other one. That ratio is what tells you percent. Okay? All right. Optical rotation and percent EV. What is rotation if enantiomer ratio is 50-50. Okay. Answer, none. Okay. All cancels. Okay. But if you have an excess of one enantiomer, okay, will rotate in that direction. Okay. All right. But let's take a step back for a second, okay? You know, let's just pretend you got, you know, a pure enantiomer, okay? And it's going to rotate to a certain degree, all right? And these things you always make in solution. Today you're going to take your mix and you're going to put it in methanol, okay? Methanol is an achiral molecule, so it doesn't affect the rotation or anything like that. So you had a solution. You've made a solution. All right? There are some other factors besides the identity of the enantiomer, okay, and the purity, whether you have one or the other. There's some other very practical, simple factors that will affect how much it rotates. And you already know this. What are those simple factors? Think back to when we did methyl violet. And we weren't looking at the degree to which something rotated. We were looking at the degree to which the light got absorbed. What were some of the things that affected how much light got absorbed? Because they do this, have the same effect on the rotation of light. Okay. I'm light. This is the chamber that it's got to come through. Every time I bump into a chiral molecule, I rotate a little bit. Okay? Rotate, rotate. All right, so what's going to affect how much I rotate? Same things from methyl violet. What affected it? What did you use the absorption of light to figure out in methyl violet? What did it tell you? Synapses. Concentration, right? The more concentrated the solution, yeah, the harder it is for the light to get through without bumping into a molecule and being absorbed in the case of methyl violet or being rotated in the case here of an N. That makes sense? So the more concentrated it is, the more it's going to rotate. So if you're gonna compare, what you find, okay, to some literature value, well, you better control for that, right? You better control for how concentrated your solution is. Okay, your solution could be 10 times, or let's say your solution could be pure, but you end up, you make a solution that's 10% the concentration that the literature value has done. Your rotation will be less, okay? And you may come to a misconclusion about that, but it's just because they made theirs more concentrated than you made yours. Does that make sense? So you got to control for that, okay? The other thing, which I don't think you do remember from the violet, is path length, okay? The distance of the light that the light has to go through, okay? If the light has to go through a longer path length, more likely it's going to get rotated or absorbed because it's bumping into more molecules as we go. Okay. Okay, so we'll control for all that stuff. We'll come up with a ratio that relates how much the light rotated versus how concentrated it was, and that's called specific rotation. And once we obtain our specific rotation, then we can compare our specific rotation to the literature specific rotation for, I think it's ethyl, it's ethyl 2-hydroxypropanoate. Yeah, that's what it is. Okay. So in the worksheet, there is a literature value for the rotation of ethyl 2-hydroxypropanoate, okay? And then you're going to figure out your specific rotation, okay? First you're going to get your rotation, then you're going to come up with your specific rotation and compare that to the literature value, okay? All right. So okay. Physical factor that affect rotation. Okay. Concentration and cell length.